After watching this video, students will be able to read the parts and understand the physical origin of photoelectronic spectra. Students will be able to identify elements from various photoelectronic spectra, and you will be able to explain why various parts of specific spectra differ from element to element. So basically, photoelectron spectroscopy, or PES as it will commonly be referred to, basically allows for the identification of information about electrons in an atom. And what it does is it takes advantage of basically the ionization capability of electrons within an atom. So we've discussed ionization energy, and we know that's the energy that's required to remove an electron from an atom. And so what we do in photoelectron spectroscopy is basically we bombard a sample with energy, so sometimes in the form of X-rays and in some cases UV. And basically that energy excites the electrons inside that specific sample. And the electrons then become ionized, they leave the sample and basically enter into a detector. In that detector, the number of electrons that are released are counted, and of course the relative energies of those electrons are measured. That then leads us to our photoelectron spectrum. Photoelectron spectra consist of several parts. On our y-axis, we have the number of electrons. Along our x-axis, we have our energy value for those specific electrons. And then, of course, we have peaks that represent the electrons themselves. Now, peak height is going to correspond to the relative number of electrons. And of course, peak position is going to indicate the relative energy of each of these electron samples. So the way that these are normally laid out is that we have the highest energy starting to the left and basically decreasing in energy to the right. Now, this is not always true for every single spectrum, and not all spectrum are in a continuous line like this. But we'll look at several examples with various types of organization. Okay, so we know that based on our electron configurations, we know that the most difficult to remove electrons are going to be those closest to the nucleus. And because of that, we know that the ones that are going to, the electrons that are going to require the most energy are subsequently then going to be your 1s electrons. Okay, so your 1s electrons are typically what's going to show up at the beginning of your spectrum. Now, sometimes these electrons, or the 1s's, will be excluded, but that will be explicitly stated in the question. Otherwise, you can assume that that first peak is going to correspond to those 1s electrons. Okay, so if we go ahead and we look at this specific example here, this is going to be our first peak. It's going to be our first peak. It has the highest energy value. So we're going to say that that is the 1s. If we go ahead and assume that that's the 1s, and obviously there are additional peaks that follow that 1s, so the implication here is that 2 electrons are being removed from this orbital. Okay, and the reason why we can make that assessment is because the additional peaks indicate that electrons farther away from the nucleus have also been removed. Okay, so again, the peak height corresponds to the number of electrons. So what I want you to notice here is that the peak height here and the peak height here are approximately equal. So the implication is that this peak corresponds to 2 electrons, and of course this peak corresponds to 2 electrons. So if this is my 1s orbital, then it's pretty safe to assume that the next electrons that are going to have the next highest energy are going to be our 2s's. Again, those peak heights are very similar, so the 2 electrons are being removed from that 2s orbital, and then of course the additional peaks that follow indicate that that must be the case. Okay, so 1s2, 2s2. Okay, if we go over to this next series, we notice that the peak height is significantly larger. In fact, it's almost, 3 times the peak height of the first 2 that we looked at. Okay, and from that we can infer that this must be our 2p. Okay, and if the peak height is triple the 1s and the 2s that we saw previously, it's pretty safe to assume that we have the 2p6s here. Okay, now that brings us to our final peak here, and of course the next farthest potential location of some electrons would be in that 3s. Now, to determine how many electrons we have indicated in this peak is going to be inferred from the peak height. So notice the peak height here is about half the height of our 1s and our 2s. So in that sense, we know that we have a 3s1 electron that has been removed in this context. So if we go ahead and we write out the electron configuration from our spectrum here, we get the following. Okay? And if we go ahead and we can compare this to the electron configuration of elements on the periodic table, we can determine that the element we see above is sodium. So when we're dealing with these problems, we want to get a feel for our x and our y axes. And my suggestion is to start with the highest energy because, of course, those are going to be your core electrons. Remember, again, the 1s is going to be the one closest to the nucleus, so those electrons are going to be held most tightly by the nucleus and subsequently hardest to remove. So because of this, we always want to kind of look out and start out with the higher energy location. Now, if they indicate to you that the 1s's are excluded, then obviously the next most difficult electrons would be being pulled from the 2s. So make sure you're paying attention to these details when you approach each and every spectrum. So let's go ahead and look at this PES spectrum that has both potassium in the purple and sodium in the black. So we've already established that our electronic spectrum here for sodium corresponds to the following electron shells and the subsequent electrons that are contained therein. Okay, but what I want you guys to notice, or I want you to look at, is the shifts that are corresponding to potassium. So remember, on the periodic table, sodium is right above potassium. Okay, so they are in the same group. However, potassium is farther down on the periodic table than sodium. So keeping that fact in mind, I want us to discuss why the shifts for potassium are different than, say, the sodium. Okay, so before we go ahead and do that, let's go ahead and identify the various peaks. Once again, we have our 1s2. It is going to be the hardest set of electrons to remove, to ionize. Okay, it's going to have the highest ionization energy. In that same thought process, the 2s2 are here. 2p6 is going to be here because, again, the peak height there is about 3 times the 1s and the 2s. Okay, so that brings us now to our 3s2. Okay, and then, of course, we're going to go to our 3p6. Okay, and then finally our 4s1. Okay, so notice that we have basically the same outline that we see with the sodium atom's peaks, except we have an additional layer of electrons. Okay, so let's go ahead and let's discuss why each of these peaks is slightly different for potassium when compared to sodium. Okay, so we know that potassium has 19 protons, okay, while sodium has 11 protons. Okay, so obviously the nuclear charge on potassium is going to be much greater than in sodium's situation. Okay, so let's go ahead and let's talk about each individual peak. Okay, so this first peak here, the 1s2, we know that these two peaks are going to be the highest in energy because they're going to be the electrons that are closest to the nucleus. Okay, so they're going to require the most energy to remove. And the reason why, of course, is because the protons inside the nucleus are attracting those electrons and they're unencumbered by any shielding. Okay, now the reason why we would see a much larger value for potassium's electrons in the 1s orbital when compared to sodium's is because the number of protons in potassium is much greater than in sodium. So the effective nuclear charge is much larger on those electrons. Okay, so more energy would be required. Okay, that same thought process, of course, is going to apply to the 2s, the 2p's, okay, as well as the 3s electrons. There is a more effective nuclear charge, there's more protons, okay, and they're subsequently going to be requiring more energy in order to be removed. Now this brings us to our outermost electrons, okay, and in this context, the outermost electron on potassium is easier to remove than the outermost electron in sodium. Okay, and this can be explained by, again, the effective nuclear charge. However, the effective nuclear charge, remember, is altered by the shielding of electrons. Now, we know that potassium has an extra layer of electrons in between the nucleus and its outermost electron. So that shielding effect is going to decrease the effective nuclear charge and subsequently make it easier for that 4s1 electron to be removed. So basically, this 4s1 electron here is farther away from the nucleus, it has more layers of electrons to shield it, and subsequently is pulled off more easily. So we now can utilize these spectrum to make assessments about electrons within a specific atom, to maybe compare some of the features in different atoms, and of course integrate that with the relative ionization energies that we've come to understand. Okay, so let's go ahead and look at another example of a different configuration for PES spectra. Basically, similar setup in terms of what we've seen. We have the relative number of electrons, we have the energy. And what I want you to notice, though, is that they have split the spectrum into two pieces, I guess, so that it can be more easily read, or at least organized in a different way. I want to point out that it is not linear, okay, and I also want to point out that the scales here are slightly different, okay. So what we see in this context is that the highest end of the scale is right here, okay, it's on that top portion, okay. Now there's no mention in this problem of the 1s orbital being excluded, okay, so of course, as we already have in the past, the 1s orbital is going to be identified as the one that's going to require the most energy to remove those electrons. Okay, so this is our 1s. The peak height is approximately 2. Okay, so there's going to be 2 electrons there. Okay, now notice that normally we would be reading from left to right. And so the thought process when you come down here might be that you'd continue from left to right. But what I want you to notice is that this portion of the chart is inverted. So basically, if you were to flip this over, okay, you would end up with a chart that follows, or a spectrum that follows kind of what we've already seen. So basically what you need to realize is that the upper end is on this end. So we know that the next orbital layer is going to still require more energy than the outermost layer. Okay, so the higher energy example here is this orbital. So this is going to be our 2s. It has a peak height corresponding to 2 electrons, so that's our 2s2. Okay, and then if we continue to go out, our next example, obviously, is going to be our 3p orbital. Now notice the height of this peak is about half the height of the other two peaks that we've seen so far. So that's going to correspond to a 3p1 electron being removed from that 3p orbital. Okay, so if we go ahead and write out this electron configuration, we can go ahead and utilize it to identify our element. So in this context, we are dealing with the boron atom. So please don't get discouraged when you see different types of organization in the PES spectra. Make sure that you're just paying attention to what the X and Y axes are indicating, and especially during these splits, make sure that you orient yourself before you start assigning orbitals.